Today's lecture is on mammography. After this lecture, students will understand the clinical importance of mammography imaging and the difference between screening versus diagnostic imaging, the challenges of mammography and the specialized equipment needed. Students will learn about the imaging equipment from the X-ray tube point of view and be able to identify and discuss its associated parts. From the object point of view, students will learn about geometric effects as well as compression and its importance to object appearance. At the image receptor end, we shall learn about the anti-scatter grid and image receptors like screen film systems and digital detection systems, and then end with a few questions. Mammography is important because approximately 1 in 8 women will develop breast cancer over their lifetimes. Mammographic exams are designed for detecting breast pathology, particularly breast cancer. Breast cancer screening with mammography helps in detection of cancers at an earlier age. Early detection is important for effective treatment. Breast cancer screening programs depend on X-ray mammography because it is a low-cost, low-radiation dose procedure that is sensitive enough to detect early-stage breast cancer. Features in a mammography image that are characteristic of breast cancer are masses, particularly ones with irregular or speculated margins, clusters of microcalcifications, and architectural distortions of breast structures. Mammography may be done for screening or for diagnostic purposes. Screening mammography attempts to identify breast cancer in the asymptomatic population and involves acquisition of 2 X-ray images of each breast in the mediolateral oblique and craniocaudal views. Diagnostic mammography procedures are performed to assess palpable lesions or evaluate suspicious findings identified by screening mammography. A diagnostic mammography examination may involve additional projections, magnification views, or other modalities like ultrasound and MRI or mammoscintigraphy. Because of the morphological differences between normal and cancerous tissues in the breast and the presence of microcalcifications, mammography imaging is more challenging than general radiography imaging. An imaging system having high spatial resolution capable of detecting microcalcifications is particularly important because microcalcifications are in some cases early markers of breast cancer. A mammography imaging system must also have high contrast resolution to be able to differentiate between normal and cancerous tissues. This is important because the attenuation differences between normal and cancerous tissue is very small as shown on the left figure. We know from our previous lectures that contrast is highest at low X-ray energies and is reduced at higher X-ray energies, so this imposes limitations on the type of X-ray tube that can be used for imaging. We can see this in the right figure where subject contrast is shown to decrease as the energy is increased. To properly image the breast, we need dedicated mammography X-ray equipment that includes X-ray detectors that have high spatial resolution and high contrast sensitivity. We will see in the next slide the type of dedicated X-ray equipment we need. Dedicated mammography X-ray equipment includes specialized X-ray tubes having special X-ray targets and filters, devices for compression, specialized grids to reduce scatter radiation, and X-ray detectors that have high spatial resolution and high contrast sensitivity. We also need phototimer detectors to control X-ray output. This figure shows a few of the components of a mammography system. The generator and operator console are not shown. For today's lecture, we shall divide mammography imaging systems into 3 main parts. The X-ray tube and its components will form one part. The object to be imaged, which is the breast, and how accessories like compression paddles and magnification devices influence the geometry and appearance of the breast image form the second part. And lastly, the X-ray image receptor with its accessories like grids, phototimers for AEC will form the third part. We shall end today's lecture with a few questions. Mammography tubes are designed with dual filament cathodes. The filaments produce focal spots of 0.3 mm or 0.1 mm at the anode target. The small filament is used for magnification imaging because it produces less geometric blurring. Because of the relationship between filament current and tube current, feedback circuits are used to adjust the filament current as a function of kV to deliver the correct tube current. Molybdenum and rhodium targets have lower tube currents than tungsten targets because of the higher melting point of tungsten compared with molybdenum and rhodium. Also note that mammography tubes are operated at lower kVs, typically up to 40 kV compared to conventional X-ray tubes that can be operated at up to 140 kV. Nominal focal spot sizes are shown on this table. 0.1 and 0.15 mm focal spots are used for magnification imaging, while 0.3 to 0.4 mm focal spots are used for contact imaging. In contact imaging, the breast is compressed against the grid and image receptor. In general radiography, nominal focal spot sizes are between 0.6 mm and 1.2 mm. Traditional targets used in mammography tubes are molybdenum and rhodium. Characteristic X-ray production is the major reason for choosing moly and rhodium as targets. Moly has K-shell X-ray energies of 17.5 and 19.6 keV, and rhodium has K-shell X-ray energies of 20.2 and 22.7 keV. For screen film imaging, the numbers of X-rays in the optimal energy range for breast imaging are significantly increased by characteristic X-ray emission from moly and rhodium targets. The top figure shows filtered beams with moly and rhodium characteristic X-ray energies. With digital detectors, tungsten is now used often in modern tubes. Tungsten targets have Bremsstrahlung X-ray energies in the 16 to 30 keV range and also have higher X-ray production efficiency and improved heat loading due to its higher melting point. Because of the wide latitude of digital detectors and the ability to enhance contrast with post-processing, characteristic X-ray production is not as important as it was with screen film detectors where moly and rhodium targets were needed. The bottom figure shows the energy spectrum for tungsten targets. Mammography tubes have rotating anodes with anode angles ranging from 0 to 16 degrees depending on the manufacturer. Tubes are usually positioned at an SID of 65 centimeters. To achieve a field coverage of 24 by 30 centimeters on the image receptor, the effective anode angle is at least 22 degrees. The figure shows two tube designs, one with a 0-degree anode angle and one with a 16-degree anode angle. Both designs feature a half-field beam geometry rather than the full-field geometry seen in general radiographic systems. On Figure B, the effective anode angle is the anode angle plus tube tilt. Also, for anode targets like molybdenum and rhodium, the tube current is low, typically between 25 to 100 milliamperes. But for targets like tungsten, the tube current can be between 50 milliamperes for small focus and 200 milliamperes for large focus. The lower tube current for moly and rhodium targets is to avoid overheating the tubes because of their low melting points. As with the conventional X-ray tube, the emitted X-ray intensity in a mammography tube decreases from the anode to the cathode side, producing the so-called Hill effect. This means to achieve better uniformity of the transmitted X-rays through the breast, the cathode side of the tube is positioned over the chest wall. The right figure here shows the Hill effect and the positioning of the cathode over the chest wall. Notice the half-field beam geometry of the mammo beam compared to the general radiographic beam to the left. If you consider the combination of Hill effect and the line focus principle, there are two effects happening at the same time for a full field beam geometry. The line focus principle means effective focal spot on the cathode side is enlarged relative to the anode side, and the Hill effect means the beam intensity is higher on the cathode side. The half beam geometry used in mammography is a way to get around this combined effect because it allows for a more uniform field and a better spatial resolution. The left figure illustrates the variation of focal spot size in the image plane for a full field beam geometry. Let's now look at the X-ray spectra from a mammography tube. As with conventional X-ray tubes, the X-ray spectra of a mammography tube is made up of Bremsstrahlung and characteristic X-rays. The top figure shows a filtered X-ray beam with both characteristic and Bremsstrahlung X-rays. The bottom figure shows plots of attenuation properties of various filter materials at different energies. To generate the optimum X-ray beam for mammography imaging, various filters like those shown on this plot are used. We shall see that in the next few slides. When X-rays exit the tube port, the X-rays are filtered by materials placed at the output port. These materials are designed to selectively filter certain portions of the beam. Because of the desire to preserve characteristic components of X-rays, certain target filter combinations are used. For example, a rhodium target and rhodium filter can be used to achieve higher energy X-rays than the lower energy characteristic X-rays achieved by either a moly target and moly filter or moly target and rhodium filter. A rhodium target and moly filter combination is not used because the moly filter removes the rhodium characteristic X-rays as shown in the bottom right image on this slide. Tungsten targets are now used for digital mammography because of higher Bremsstrahlung X-ray production efficiency and higher tube loadings than moly and rhodium targets. However, an unfiltered tungsten X-ray spectrum also contains a large fraction of unwanted L characteristic X-rays. These are removed by using rhodium and silver filters as shown in the figure on this slide. In some cases, aluminum filtration is used, but that requires using thicker amounts of aluminum than rhodium and silver filters because aluminum has a lower atomic number and no useful K absorption edge. Aluminum filtration is typically used in digital breast tomosynthesis because it provides a larger fraction of higher energy X-rays. The high energy X-rays do not degrade contrast because the tomographic reconstruction process provides enhanced contrast. Breast compression is important in mammography because it reduces scatter reduction, geometric blurring, and results in reduced dose to the patient. The breast is typically compressed with a plastic paddle, resulting in a reduction in breast thickness and also spreading of the breast so that there is less overlap of anatomy. Compression also reduces inadvertent patient motion. The compression paddle exerts a force of between 25 to 44 pounds. In some situations, spot compression is used for further thickness reduction and to focus on a smaller area of the breast needing more attention for improved contrast and reduced anatomic overlap. Compression paddles are driven by automatic foot pedals, but there is also a capability of finer manual adjustments. A safety feature allows the compression paddle to be automatically released following an exposure, or it can be released by pushing a button. The top image shows a spot compression image. The bottom figure shows illustrations of breast compression. Beam quality is important in mammography to ensure the beam is optimized for the best image quality at the lowest possible dose. Beam quality is characterized by half-value layer. The half-value layer depends on the kV and filtration in the beam. Half-value layer ranges from 0.3 to 0.7 mm of aluminum for the kV range and combinations of target material, and filter thickness used in mammography. Breast compression paddles act like beam filters, so are included in the calculation of the half-value layer. The plot in the middle shows some half-value layers at different kVs for the various target filter combinations. Table 8.2 shows the minimum prescribed half-value layer requirements for different tube voltages according to MQSA regulations. Table 8.3 shows the maximum half-value layer limits recommended by the ACR. Tube output is the measured beam intensity normalized per mass or per 100 mass. The units of beam output are milligray per mass or milliröntgen per mass. In measuring beam output, the kV, the target, the filter material and thickness, distance from the source, and the focal spot size must all be specified. X-ray tube output is useful for calculating the free in-air incident air camera or exposure to the breast from a mammography system. Once exposure is known, average glandular dose to the breast can be calculated. Tube output rate is the air camera rate at a specified distance from the focal spot and depends on the tube current and an extended exposure time. Typically, the settings used for measuring the tube output rate are 300 mass at an exposure time greater than 3 seconds. MQSA regulations require air camera rates of at least 7 milligray per second at 28 kV for moly-moly mode at any SID for screen film systems. For digital detectors, the manufacturer's requirement specified in their QC manual is used. X-ray tube and collimator alignment are important to ensure that the X-ray tube central axis is perpendicular to the plane of the image receptor and intercepts the image receptor at the correct location near the chest wall. This protects the patient from unnecessary radiation exposure to the lungs and torso and also includes as much breast tissue as possible in the image. Collimation of the X-ray beam is achieved using fixed-size metal apertures or adjustable shutters. Tube alignment with respect to the image receptor must be verified during acceptance testing of the system and after X-ray tube replacements. Specific collimation requirements are listed on this slide. MQSA requires that the sum of X-ray field and light field misalignments on opposite sides must be less than 2% of the SID. Another MQSA requirement is that X-ray field must not extend by more than 2% of the SID at any one of the four sides of the image receptor. The radiation field must extend to the chest wall side of the image receptor, but not beyond the image receptor by more than 2% of the SID. Another MQSA requirement is that the anterior edge of the compression paddle must be aligned just beyond the chest wall edge of the image receptor so it does not appear in the image. The paddle must not extend beyond the chest wall side of the image receptor by more than 1% of SID. MQSA regulations require repairs to be made within 30 days if the light and X-ray field alignment, X-ray field and image receptor alignment, or compression paddle alignment is out of tolerance. As I mentioned in a previous lecture, because we are imaging with a point source, the X-ray beam spreads out as it makes its way to the image receptor. As it goes through the patient, various objects of interest in the patient can be magnified depending on their distance from the image receptor. This distance is called the object to image receptor distance OID. OID, source to object distance SOD, and source to image distance SID are all related. Let's look at these relationships and how the geometry of image acquisition affects magnification of objects in the patient. Magnification is a geometric effect. As with any type of projection imaging, by moving the object location relative to the point source and image receptor, different levels of magnification can be achieved. The SID is equal to SOD plus OID. When SOD is equal to SID, magnification is 1 and the image represents the true size of the object. This example shows how to calculate magnification for the SID and SOD numbers shown. Moving the patient too close to the source will result in increased patient exposure, increased magnification, as well as increased focal spot blur. Magnification in mammography is achieved by placing a breast support platform called a magnification stand at a fixed distance above the image receptor. A small focal spot is used to reduce geometric blurring. The anti-scatter grid is removed and the breast is compressed. The advantages of magnification are an increased effective resolution of the image receptor by the magnification factor, reduction in image noise relative to the object being rendered, and a reduction in scattered radiation. The best resolution is on the anode side of the field. Typical magnifications are 1.5, 1.8, or 2 times. There are some limitations when magnification imaging is used in mammography. Even with a 0.1 mm focal spot, magnification can produce geometric blurring. Because of the small focal spot size, there is also a tube current limitation. With the use of the magnification stand, the breast is closer to the source of radiation, but this increased dose is offset by the removal of the grid, which reduces the Bakke factor by 2 to 3. In screen film imaging, scatter reduces contrast. In digital mammography, the main effect of scatter is not contrast reduction because contrast can be adjusted by post-processing methods. Rather, contrast reduces signal-to-noise ratio by adding random noise to the image. We can reduce the scattered radiation reaching the image receptor by using an anti-scatter grade or air gap. Grades in mammography transmit about 60% to 70% of primary X-rays and absorb 75% to 85% of scattered radiation. On this slide, we shall first talk of the linear focus grid. This is shown in figure A above. This grid has typical frequencies of 30 per centimeter to 45 per centimeter and a grade ratio ranging from 4 to 1 to 5 to 1. Grades oscillate during exposure to avoid grade line artifacts. For mammography grades, the Bakke factor is between 2 to 3, leading to doubling or tripling of the breast dose, but the benefit is improved image contrast by up to 40%. An advantage of digital detectors is that even with the extra radiation needed because of the use of a grid, the Bakke factor is about half of that for screen film systems. The bottom figure shows the relationships between scatter to primary ratio and breast diameter. We can see that the scatter to primary ratio increases with increasing breast thickness and diameter. Another great technology is the cellular grid. This grid allows scatter rejection in 2D and has about 15 cells per centimeter. It has a grid ratio of 3.8 and requires specific grid motion during image acquisition. Cellular grids provide better contrast improvements than linear grids because of a 2D scatter rejection and presence of air interspaces. The cellular grid is shown in figure B above. Another method of scatter rejection is the use of an air gap technique. This method reduces scatter by increasing OID. This, however, leads to increased breast dose and increased focal spot blurring. This increased dose can be offset by using a sufficiently large air gap because no backing factor comes into play when no grade is used. In screen film systems, the best contrast in mammography film occurs at the linear portion of the HD curve. There is significant reduction in contrast on the toe and shoulder portions of the curve. Even with optimal contrast, anatomic information in dense glandular breast tissue and at the skin line may not be visibly rendered. Digital mammography has several advantages over screen film systems. Aside from the wide dynamic range and wide latitude of a digital system over screen film, digital detectors also require less exposure because of higher sensitivity in the low exposure regions. There is also increased productivity and patient throughput when digital image receptors are used. Image quality is also improved and lesions are more conspicuous because of post-processing. The figure shows the curves for screen film and a digital detector. Let's look at the technology for digital mammography. Digital mammography is built around a thin film transistor active matrix array. There is an indirect detection system that uses a cesium iodide scintillation phosphor to convert X-rays to visible light, and a direct detection system that uses amorphous selenium to convert X-rays directly to charge. A third technology based on a photostimulable phosphor uses a dual-side readout computed radiographic CR system in place of a screen film cassette. Image quality and signal-to-noise ratio is lower for CR-based systems than for thin film transistor array detectors. All three technologies are shown on this slide. When mammography was acquired using screen film systems, we had to deal with film processor QC on a daily basis. With digital detectors, there is a different problem to contend with. Digital detectors can potentially have malfunctioning detector elements, column and line defects, and variation in gain across the detector area that can cause artifacts in images if not corrected. Manufacturers use pre-processing algorithms to correct these defects. Correction is done by using a flat field correction image, which is normalized and inverted as an inverse gain map. These maps are stored in the system and applied to each image acquired under similar conditions. The for processing image shown on top is a raw image dataset that is used by the computer-assisted detection algorithm. Before it is passed on to the for presentation stage, a nonlinear algorithm is applied to perform various equalization and delineation tasks. The presentation image shown at the bottom has contrast and spatial resolution enhancements applied before it is presented to radiologists for viewing and diagnosis. Both for processing and for presentation images should be saved as part of the patient exam if CAD applications or other image processing is to be applied. For presentation images cannot be unprocessed once processed. Let's finish up with a few questions. First question, which of these is not true about mammography imaging? First choice, cellular grids reduce more scatter radiation than linear grids. Second choice, the anode side of the tube is positioned over the chest wall. Third choice, tungsten targets have higher melting points than moly targets. Fourth choice, rhodium-moly target filter combinations are not used in mammography. The statement which is not true about mammography imaging is B. Next question. When a patient is imaged in the mammography department, the most likely grade ratio in the anti-scatter grade is first choice 8:1, second choice 10:1, third choice 5:1, fourth choice 12:1. The correct choice is third choice 5:1. Next question. Match the letters to the components shown on this image. Components are compression paddle, X-ray tube, collimator, X-ray detector, grid. The correct component matches are E, C, A, D, B. Thank you for watching this presentation.